And now for the final part of this lesson, before we get into the exercises, of course, what happens when we have two improper limits where one is going to an infinity, positive or negative, and the other one causes the function itself to go to a positive or negative infinity? Oh my goodness. Well, that's what we have going on here. Same instructions as the integral converge or diverge. If it converges, evaluate the integral. So we've got ourselves 3 over x cubed. It looks like this. And we're looking at the, integral from 0 to infinity. So it'll be all this area right here and all that area right there. So what do? Well, we have two places, two regions, boundaries that give us issues, 0 and infinity, so we need two limits. And then you could split up this integral any way you want. So we could split this anywhere, so I'm going to split it at 1. So you could write it as that, just because 1 is a fairly easy number to plug in. And that would be plus the integral from 1 to infinity of 3 over x cubed dx. So let's rewrite it with two limits. So we'd have the limit as a goes to 0 from the left, right? Because we're going from left to right. Sorry, from the right, just kidding. From the right, since we're going from left to right, we only get the right side of 0, right? And you can see that from this picture. So that's going to be from a to 1. And again, 1 is what we just chose. Plus, and now we're going to have a second limit. The limit as b goes to, in this case, we're going to infinity. And that would be the integral from 1 to b. And that would be of 3 over x cubed dx. Now, as before, it will be so now. If one of these two integrals diverges, we're done. If they both diverge, so be it. But we really only needed the one to diverge to tell us that we're done. If one, the first one that we check converges, then we got to check the second one. And if that converges, then we converge. If it diverges, then we diverge. Okay, let's do this. So we're going to integrate this like normal. We get the limit as a goes to 0 from the right. And that's going to be, I'm looking at that as 3x to the minus 3. You add 1 to that. And we're going to get 3x to the minus 2 all over minus 2 evaluated from a to 1. And again, only evaluate this one, because if it diverges, there's no reason to check that one. So we get the limit as a goes to 0 from the right-hand side of 0. I'm going to rewrite this as 3 over negative 2 times x to the second in the denominator, negative exponent. So we get a to the second. Eventually, once we plug that in second, we're going to first plug in 1. Upper bound minus lower bound, so that would be that, minus 3 over, and then we've got the negative there, don't forget about that, negative 2 times a to the second. So essentially you're doing the first fundamental theorem. The only difference, you got a limit, and one of your bounds is a letter. Okay, so now let's evaluate this. This first value right here is going to be negative 3/2. That's fine. Minus a minus is going to be plus 3 over 2 times, now essentially what's happening here is we've got 0 from the right-hand side squared. Well, that's a constant over 0, or a really, really tiny number. Well, that's going to go to infinity. So it's like you got negative 3/2 plus infinity. And so therefore, that's a therefore sign, the integral diverges. All right, what's happening here is this curve is not going quickly enough to the vertical asymptote to limit the area from going to infinity. So we're getting an infinite area here, and this might very well converge. But a converging value plus a diverging infinite value, infinite. That's why we only had to check the first one. All right, that's it. A short one, a quick one. I'll see you on the flip side for some exercises. We'll get some good variety. It'll be fun. Peace.